We started with inverse trig functions last week. We've also done a few identities. In chapter 6, we did a couple of basic identities. We did the reciprocals and a couple others, really basic ones. Today we're going to introduce some more identities. We're going to use them a little bit today, but not a whole lot. We're also going to be technically doing some inverse kind of things, but our restrictions that we had for the inverse trig functions we did last week are not necessarily going to apply today. And it's one of those things you kind of have to know when to use them and when not to use those domain restrictions. And you'll kind of see the little bit of a difference today. So we're going to start with the Pythagorean identities. Okay. The Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So, and remember, when you see the power, when you see a power written like that, that means that we have the sine of theta squared. When you put the power on the trig function, it's another way of saying, hey, I'm taking the sine of that object and then I'm squaring that whole thing. It's just a shorthand way to do it. I don't know where it came from. I actually kind of like it though. So this is sine squared theta plus the cosine of theta squared is equal to 1. And this is true for any angle at all. I don't really want to do it today, but we will at some point. I'll do a proof to show you where that one comes from. It's actually a fairly simple proof to do. But that's called the Pythagorean identity. The reason is it comes from the Pythagorean theorem. Okay, it comes from the Pythagorean theorem. So that's all that is. Now, we can put some adjustments to it. If we divide everything by cosine squared theta, divide every single object by cosine squared theta. Well, sine divided by cosine is tangent, cosine divided by cosine is 1. 1 over the cosine is the secant. So that changes it into tangent squared plus 1 equals secant squared. This is still a Pythagorean identity because we took the basic one and did a simple change to it. And by the same token, if we divide everything by sine squared, you get a similar Pythagorean identity of 1 plus the cotangent squared equals the cosecant squared. Why do we want to use the identities? Because at times you need to do substitutions and stuff to be able to solve trig equations. We're going to use a couple of these today. Not a lot, but we're going to use some today. That's really what identities are for. Somebody came up with the first one, sine squared plus cosine squared equals 1. That's a relatively simple one to come up on its own without connection to something else. The other two identities follow from that one. And they're simple to come up with. Divide by this, divide by that. And why do we do that? Because sometimes we have complex trig functions. We want to simplify them down by using these identities. And we're going to do a lot more work with identities when we come back from the break. Okay. So, going to kind of get away from that. Going to come back to it eventually. But here's what we're doing on this next few. We're solving in radians, find all solutions to every single equation. All possible solutions. Not just within a particular range, because when we were doing the inverse trig functions the other day, we solved it within a particular range. Right? We're not doing that. We're coming up with every possible solution. How many angles do I take can I take the cosine of and get root 2 over 2? Yeah, because you can just keep going round and round and round, and you can go round and round and round the other way. So there's technically an infinite number of solutions. We are going to put down every single one of those. I'll show you how. I'm glad you asked, because that's what this is about. Okay, so in your unit circle, how many angles just between 0 and 2 pi? How many angles actually do I take the cosine of and get root 2 over 2? There's 2 of them. What are they? Pi over 4 and 7 pi over 4. Those are 2 within the unit circle, within your standard 0 to 2 pi. So if we're dealing with all the possible solutions between 0 and 2 pi, those are my answers. However, we're not dealing with all that. We're dealing with everything else. And here's what you do. You say, I'm going to take those and add to that 2n pi. Let me explain what that means. Well, 2n pi is 2 pi, right? Times n. And n is an integer. N stands for any integer value. 0. If I put 0 in for n, what do I get? I get these two. If I put 1 in for n, what do I get? I get these two plus 2 pi, which means I take the first one, go around the full circle. I take the second one, go around the full circle, and I get it. If I do it times 2, that means I go 4 pi. So I go here and I go 2 pi, 4 pi. Because every 2 pi takes me around one loop of the circle. Let's say I put in -1. So I start here at pi over 4, and I go backwards one full circle. So n is an integer. Any integer value times 2 pi added to either one of these will give me every single possible angle where I take the cosine of and get root 2 over 2. I have listed an infinite number of answers. Every single possible solution is here. N is an integer. So any integer value times 2 pi will give me that. Why don't we put the n in front of the 2 pi? Standard operating procedure. Number of variable pi's go at the end. It's just the way you list things. Okay? So I've listed every single possible, an infinite number of solutions there. That's what I've done. So I've covered all the basics. Every single answer. I have an infinite number of solutions written down. Didn't think I could write them all, did you? Okay, so the next one. Same idea. The next one's a little more difficult, though. 2 sine theta plus 1 equals 0. Get the sine theta by itself. Subtract 1 divided by 2. Sine theta equals -1/2. Whoa. Subtract 1 divided by 2, you get sine theta equals -1/2. So, what value, where do I have on your unit circle? Do you have the sine of theta equal to -1/2? Sorry, -1/2?
7 pi over 6.
7 pi over 6. 7 pi over 6, not 7 pi 6. 7 pi over 6 and 11 pi over 6. So those are the two within the unit circle. But I need to add to that all the possible circles going around, which means that I need to add to that 2n pi. And if n is an integer, that gives me an infinite number of solutions, because the integers are infinite in size. A gazillion times 2 pi circles around. My arm would fall off trying to demonstrate that, but you get the idea. Next one's a little bit more difficult because on your unit circle, you do not have directly you do not have the tangent is not a particular value, but you have to figure out which one it is. Okay, so the tangent of -3, that means the sine and cosine are not the same sign. And it would be the one where you have the root 3 over 2 over the 1 over 2. So the sine would be root 3 over 2 and the cosine would be 1/2. Where do you have that happen at?
Pi over 3. Wait, this side.
It has to be one has to be positive, one has to be negative. 2 pi over 3. Is there another one in the unit circle that does that?
Yeah.
Which one is it? 5 pi over 3 also does it. However, there's a very important thing right here. Tangent is every pi, not every 2 pi. So we only have to come up with one. And then n pi to that. Because if I add a whole pi, if I add 1 pi to that, 2/3 plus 1 is 5/3. That gives me my 5/3 pi. And then if I add another one to that, because the tangents are always opposite each other. Every tangent value is always opposite each other no matter where you're at. So I got one here, I got one there. They're complete opposites each other, which is really kind of cool. Cotangent does the same thing. So I don't have to add 2 pi, I only have to add 1 pi, or 2 pi, or 3 pi, or 4 pi. Integer pi's, odds, or evens, it doesn't matter. So n pi, figure out one of them, and add n pi to that, and you've got them all. Okay, so tangents are actually a little easy. You only have to come up with the first one, and then add pi to that, n pi. So, next one, what's my first step? Divide both sides by 4. Get cosine squared theta equal to 3/4. Do I have the cosine theta?
Yeah.
No. I need to square root both sides because cosine squared theta is cosine of theta squared. So I square root both sides. And that gives me the cosine of theta equals √3/2. And how often does that happen at? And actually, I got to be careful on this one. Because when I take the square root to solve, it could be plus or minus. Right? It could be plus or minus. Because when I square both sides, to get cosine squared to work my way back to the original equation, I got to think about that. So how many places do I have plus or minus √3/2? Got 4 places on the unit circle. You need to list all 4. Pi over 6. 5 pi over 6. 7 pi over 6. 11 pi over 6. And then to those, I need to add 2n pi to list every single possible infinite number of answers. Boy, I had to write twice as many infinite solutions on this one. Did you understand that you can have infinite groups that are smaller and larger than other infinite groups? Infinite does not necessarily mean that there is no size to the group you were talking about. Okay. For example, all the group of real numbers is infinite in size. So is the group of integers, but which one's bigger? All real numbers, because it has stuff that aren't in the group of integers. Yes, infinite groups are not all the same size. You just can't count them. Okay, questions? Okay, we're doing a use of. Use of. Okay. When you get to second semester calculus, U-subs will be a very big deal in one of the parts you're doing there. It's not nearly as big a deal today as it will be in there. U-subs will be a big one. Okay. Now we're doing something fairly simple here. This is a fairly simple set of U-subs that we're doing here today. Okay. The idea is to replace something scary with something nice. That's the whole idea behind a U-sub. Take something scary, something complicated, something difficult, put something easier in its place, and work with the easier thing, and then put the scary thing back in later when you're done. Take a difficult problem, make it an easier problem. work with it as an easier problem, and then go back to do the difficult stuff after you get done doing the easier stuff. Really is a simple idea to do. Okay. So let's take a look at this one here. The idea would be to do a U sub here would be to take and replace something difficult with something easy. They're not that big a deal on this one here, but the idea would say, okay, instead of 2 theta, let U equal 2 theta. Okay, let U equal 2 theta. So instead of solving the sine of 2 theta equals something, say, oh, I want to say the sine of U equals negative root 2 over 2. That's what I'm going to do. I'm going to say let U equal this, let the sine of U equal that instead of the sine of 2 theta. That's my substitution. Usually when you do something like this, it's whatever's in parentheses or inside a radical or something like that. That's what you'll be doing a lot of. Like I said, when you're doing it next year in calculus, it's a different reason for doing it, but it's the same concept. Okay, what values of U do I take the sign up to get negative root 2 over 2? Where does that happen on your unit circle?
5 pi over 4.
So U equals 5 pi over 4. And where else?
7 pi over 4.
And 7 pi over 4. And then I can do the plus or minus, but I don't want to do the plus or minus right away. So U equals those values, plus or minus 2n pi. However, well, actually, yeah, I do want to go ahead and do that now. So I want to take these. Let me do it this way here. 7 pi over 4 equals plus 2n pi. That's my solution for U. However, did I start my problem with U? No, my original variable was not U. My original variable was theta. I need to solve for theta. But what does U equal? U equals 2 theta. So I go, oh, wait. U equals 2 theta. That means 2 theta equals 5 pi over 4 and 7 pi over 4 plus 2n pi. Now I can solve for theta. How do I solve for theta?
Divide by 2.
Divide by 2. Divide everything by 2. Which means theta equals 5 pi over 4 divided by 2 is 5 pi over 8. 7 pi over 4 divided by 2 is 7 pi over 8. And then plus, and I have to divide everything by 2. N pi. Solve for U. U is easier than solving for 2 theta and then substitute it in. It could be something much more complicated than, let's say, 2 theta. I could be doing the sine of 2 theta plus 5. And I'd want to do a U sub for that and then put, 2 theta plus 5 back in and then do everything I need to do to solve for theta. It could be much more complicated. It's not going to be much more complicated for you guys here at this point. But this works for very complicated things. I can do that with very complicated ideas. Give number 6 a shot. Okay, first step. Well, you have choices for your first step. What I would do first is get the cosine of pi over 3 by itself first. That's just me. Cosine of theta over 3 equals negative 1/2. And then let U equal theta over 3. So the cosine of U equals negative 1/2, which means that U equals, and negative 1/2 takes place at 2 pi over 3 and at 4 pi over 3 plus 2n pi. But once again, I don't have U. I have theta over 3. So I do my reverse substitution. Put theta over 3 in here. And how do I solve that? Multiply everything times 3. Theta equals 3 times that. Ooh, that's 2 pi. And that's 4 pi. And that times 3 gives me plus 6n pi. Okay? Questions? All right. Okay. First thing you need to notice. Find all solutions on the interval from 0 to 2 pi. Is 0 considered a possible solution?
Yes.
Yes, because it's included. Remember, brackets means the answer is included. Is 2 pi a possible solution? No, because parentheses means that it is up to but not including that point. Remember your interval notation. So am I listing an infinite number of solutions? No, I'm not listing an infinite number of solutions. I'm just coming up with all possibilities between 0 and 2 pi, including 0. So I don't have to worry about the plus 2n pi or any of that crap. I don't have to worry about any, just my restrictions are within the unit circle. Anything in the unit circle, it'll work. So the first one, oh, hey, looks pretty bad, doesn't it? But what do I have? What kind of equation do I have? Nope. You don't want to do yourself on this one. I have something squared plus something plus a number. I have a quadratic equation. However, instead of x squared, I have sine squared. But I have a quadratic equation. If that were 2x squared minus 3x plus 1, you would factor it. You factor this just like a quadratic, because I have sine squared minus sine and some number. So I have a quadratic equation with sine theta instead of x. So I factor it as such. So I have 2 sine theta minus 1 times sine theta minus 1 equals 0. Set each one equal to 0. Because that's what you would do in a quadratic, right? 2 sine theta minus 1 equals 0. Sine theta minus 1 equals 0. So that means the sine of theta equals 1/2. And the sine of theta equals 1. And then where are those values on your unit circle? That the sine equals 1/2 and the sine equals 1.
Pi over 2 and 3 pi or pi over 3 and
pi over 3, pi over 6.
What?
You're looking at the cosine.
Oh, remember that, pi over 3. Or sorry, pi over 6.
Pi over 6 and 5 pi over 6.
5 pi over 6.
So I have 3 solutions. Unlike a quadratic, which would only have 2 solutions, but that's what it is. It's a quadratic equation with sine instead of x. So x squared, instead of 2x squared plus 3x minus 3x minus or plus 1, I have sine squared. Sine. I just factor it like a quadratic. Okay. Questions? So these are solving equations. You have to think about them as solving an equation, and you have to go along those lines. So on the next one, what's my first step on the next one? Divide by cosine.
Oh. But it doesn't equal 0.
Oh.
Okay. It might equal 0. We don't know for sure. And if you divide by 0, you cannot divide by 0. The cosine of theta might be 0. You can't divide by something that might equal 0. Okay, so what you have to do is you have to do something else. Set it equal to 0. Yep. 6-letter F word factor. Okay. So set it equal to 0. So subtract cosine theta from both sides. Tangent of theta, cosine theta, minus cosine theta equals 0. Now, 6-letter word that starts with an F. Factor. What do I factor?
Fired.
Factor out the cosine. What do I have that's the same in both terms? Common factor. Pull out the common factor. So I have the cosine of theta times tangent theta minus 1 is equal to 0. Pull out the common factor. And now set each factor equal to 0, just like we set each factor equal to 0 here. Cosine theta equals 0. Tangent theta minus 1 is equal to 0. Where is the cosine of 0?
Pi over 2. Negative pi over 2. 3 pi over 2.
Pi over 2 and 3 pi over 2. So this one gives me pi over 2 and 3 pi over 2. And then I add 1 to both sides, so I get the tangent of theta is equal to 1. Where are the sine and cosine the same values?
4.
Pi over 4 and 5 pi over 4. And that's my solution. You with me so far? Questions? So, when you're working problems like these, don't think of them as sines and cosines. Think about them as x and y's and stuff like that, rather than, oh, I want to solve for this. No, you want to do a few steps before you get to solving for the cosine or the sine. When I see something like number 7, I think, ooh, quadratic, something squared, plus or minus something, plus or minus some number. That's a quadratic equation. If I have an object squared and that same object not squared and then a number, that's a quadratic equation. Often what you always want to do is set things equal to 0. So on the next one, I set it equal to 0. Ooh, I have the same thing in both terms. Pull out that common factor, that common thing, which happens to be in this case, cosine theta. Yes? You could, but you want to start, it's one of those things that you start getting into dangerous territory when you're doing that. But if it helps you see what I'm seeing here, you could do that. It's like, oh, instead of sine, let's put in an x for everywhere there's a sine. Or put in an x for everywhere there's a tangent, and a y for everywhere there's a cosine. You can go ahead and do that and then manipulate it and then put it back in. So you're basically doing a U sub of sorts, and you could do that. That would work fine. Be careful so you don't lose what you're actually trying to talk about and which one's which. Yeah, you could do that if that's what you want to do. But you have to start saying it's this object squared and that object rather than just x or y, because what are x or y? They're just another object. We're using sines and cosines instead. I've seen ones like this with logarithms. I've seen ones with it like this with even more complicated things. You may or may not, depending upon how far you go, but it's being able to visualize and see this stuff is what's going to make a difference. And sometimes you know, you may not be solving things, you may just be simplifying them to a point where you can actually work them a little easier. That's a lot of calculus, is actually working things to make them an easier thing to work with by doing substitutions and stuff like that. Trig identities really help for making things easier to work with. Okay. I want you to try to do number 9 on your own. If you really hazard to try to guess on 10 and 11, you might want to, but I strongly suggest you wait for me to show you. Okay, so if you didn't see it right away, once again, like I said, if you wanted to, you could let u equal the cotangent of theta, which would give you u squared plus 2u plus 1 is equal to 0. Do you see quadratic now? Yeah. And this is actually u plus 1 squared is equal to 0. Okay. So put cotangent back in. Cotangent of theta plus 1 squared is equal to 0. Cotangent of theta plus 1 equals 0. Cotangent of theta equals -1. Where does that equal -1? 3 pi over 4 and 7 pi over 4, where the sine and cosine are the same, just opposite signs. 3 pi over 4 and 7 pi over 4. Now the next one's a little bit harder, because although I do have a quadratic in there because I've got sine squared, I have sine squared and I have cosine. I do not have the same object, so I don't technically have a quadratic as it stands now. So what we need to do is we need to do a substitution. We need to go back to the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. So sine squared theta equals 1 minus cosine squared theta. Go back to the original one, and we get sine squared theta is equal to 1 minus the cosine squared theta. Subtract cosine squared theta from both sides in our original Pythagorean identity. And then substitute this in for this. Cosine theta plus 2 is equal to 2 times 1 minus cosine squared theta. Distribute the 2. Cosine theta plus 2 equals 2 minus 2 cosine squared theta. Move the 2 cosine squared theta, or actually subtract 2. Add 2 cosine squared theta. I know that's getting nasty. 2 cosine squared theta plus cosine theta is equal to 0, because 2 minus 2 is nada. Now what? Nope, it's not a quadratic. It is, but I don't have 3 terms, so I can't factor it that way. Pull out the common term. Pull out the common factor. I have cosine squared and I have cosine. Here I have 2 cosines, there I have 1 cosine. Pull out a cosine. Cosine theta times 2 cosine theta plus 1 is equal to 0. Pull out the common factor. Cosine theta is equal to 0. 2 cosine theta plus 1 is equal to 0. Cosine theta is equal to -1/2. So where's the cosine 0? And where is the cosine equal to -1/2? Pi over 2, 3 pi over 2, 2 pi over 3, and 4 pi over 3. this is part of what you need identities for. It's to solve when you have a situation like this. Do a substitution. Okay. This is actually the Pythagorean identity of a big one. Sine squared, cosine squared, 1. It's a big one. And if you ever want to do something on your calculator, take the sine of an angle squared plus the cosine of an angle squared and add them together. And you will get 1 no matter what the angle is. It's kind of cool, actually. So, number 11. It looks like a quadratic. Secant squared plus tangent equals 3. Once again, though, I have secant and I have tangent. I want to put them into the same thing. Now, I could try to substitute for tangent theta. If you go back and look at your Pythagorean triples, you have the secant squared is equal to the tangent squared plus 1. I could solve that for tangent and put that in for the, in terms of secant, put that in there. But then I'm dealing with square roots and crap, and nobody wants to deal with square roots and crap. I have a secant squared equals something in terms of tangent. I can just get rid of the secant squared and have tangent only in one shot. Secant squared is equal to tangent squared plus 1. Okay, from your Pythagorean identities. So that's what you do. Replace secant squared with tangent squared plus 1. And then I have plus the tangent of theta is equal to 3. Set that equal to 0 and rearrange it. Tangent squared theta plus tangent theta minus 2 is equal to 0. Yes?
How did you get the plus 1 over on the cosine one?
Because when I pull out a factor of a cosine.
Oh, okay, okay.
If you have 2x squared plus x, and you factor out an x, what do you have? You have 2x plus 1.
Oh, okay.
When the term that you factor out is one of the terms, you have to have a 1 there to mark the place.
All right.
Same thing on that one. Okay, and this is a quadratic, x squared plus x minus 2. So that gives me tangent plus 2, tangent theta plus 2, tangent theta minus 1 is equal to 0. So that means the tangent of theta is equal to negative 2, and the tangent of theta is equal to 1, and we have some issues here. Okay. From your unit circle, tangent of theta, where's tangent theta equal to 1? Pi over 4 and 5 pi over 4. So this one's not too bad. Pi over 4 and 5 pi over 4. That is where the sine and cosine are the same. Are there any places where the sine is twice as large as the cosine on your unit circle?
No. Wait.
Are there any? There are no places on your unit circle where the sine is twice the value of your cosine. Nowhere. Where it's twice as large. So there's no place on your unit circle where the tangent of theta is equal to negative 2. Does that mean you can't solve it? No. That means you got to whip out your calculator. And do the inverse tangent of negative 2. If you know where your tangent key is, the inverse tangent is right above it. You'll have to hit second or shift or whatever to get the inverse tangent of negative 2. And you'll get a decimal, right? Ooh, you got what, negative?
Yeah.
Is that what it's giving you? Is that between 0 and 2 pi?
Oh, so it's going to be...
So what do you need to do to put that between 0 and 2 pi? Add pi to it because the tangent cycles every pi, not every 2 pi. Add pi.
2.0344.
Yeah, so you'll get 2.034. That's good enough. Now it cycles every 2 pi. Or every pi, not every 2 pi. So add another pi to it. See if you get a number that's between another number between 0 and 2 pi.
5.18.
Yeah, 5.18. Is that less than 2 pi? Yeah, 2 pi is 6.28. 3.14, 6.28. So yeah, so you do get two numbers. 5.176. Yeah, isn't that fun? It is doable. If you want to, if you can use values off the unit circle, you use values off the unit circle. Those are exact values. Pi over 4, 5 pi over 4 are exact values. Anything else is an approximation. So these other ones are approximations. I mean, I only rounded off to 3 decimal places, but your calculators went until there wasn't any more room, right? Which means that it's still going and there just isn't any more room on your computer. But your calculator is just a little mini computer. And you want more decimal places, you need to get on a computer that will run 2 large decimal places.
Is it infinite or will it?
I think it's infinite. I think these ones are irrational solutions. They go on forever and never repeat. I do believe that this would be an irrational one. Yes.
So why is the tangent of theta plus 2 and not minus 2? Because it's minus 2 up there.
Because when you FOIL it out, you have to when you factor is a negative 2 plus or you have to have 1 and 2, and one has to be positive, one has to be negative. That's why it's plus 2 and minus 1. Questions? Okay.